Okay, running a little bit late, sorry. So this question came up about the hydrogen atom states that we were studying, especially the angular momentum state, the angular portion of the wave function of theta at phi. Spherical harmonics, they're called the YLMs. And we were talking about how those express angular momentum in quantum mechanics. The relationship of those functions, one part of the wave function to the angular momentum of the ensemble. And so that prompted the question about the discreteness. Can we go back and understand why the quantum levels in the hydrogen atom are discrete? So this takes us back to chapter 1. This is a figure in chapter 1 talking about the Bohr quantization condition. Might go back to chapter 1 to review this as a page on the Bohr quantization condition, which was an early attempt to try to understand quantization in the hydrogen. And so this figure has, some kind of wave traveling around a circle, right? It's kind of an imaginary thing. So the wave traveling around the circle. And the idea is that the circumference of the circle was matched by some integer, some multiple of the wavelength, the wave. If that happens, then the wave will be kind of constructively interfering with itself as it travels around the circle. And that led to quantization that was, in fact, like the angular momentum quantization, only not as complete. The idea that a wave traveling around the circle may be like a wave traveling around a proton would lead to some kind of resonance. There had to be some matching number of wavelengths around the circumference. That to kind of fill this out a little bit. Yeah, fill this out a little bit, then he had down further on that page. Had this idea of a wave traveling around the circle, and if it doesn't match itself, then there's a discontinuity in the wave, and so there would be a mismatch, and it wouldn't resonate with itself. Whereas if it matches, then the wave would travel around the circle, and we have a resonating condition. So this is the early idea of Bohr. There was some kind of resonant condition. So we find that to be true in these spherical harmonics. That expresses a resonating condition of the wave on the sphere. So fully three-dimensional, two-dimensional. Okay, so in other words, there's something about the guiding wave structure which resonates under certain conditions, and that's what leads to the discrete levels, discrete energy levels. The wave functions that have that kind of resonating condition are the ones that we get from the pure modes for the hydrogen. So that was a good question. You might want to go back and read that 1 or 2 pages there in chapter 1 to see how that was kind of an early idea that gets expressed more completely in solutions to the Schrodinger equation. Yeah.
So that's why it has this. So that's why it has discrete. The average has discrete average for orbit.
There's
hydrogen atom.
That's part of it. There's also the radial condition. The other thing is that you're confining the electron to a region near the proton because it's attracted to the proton. So the attractive 1 over r potential is also confining the electron to the radius from the proton. So there's another quantization, which is the principal quantum number relates to that. Again, relates to that confinement. That's kind of like what we saw the particle in a box. Was that as long as you confine the electron to some region, then you get a quantization. You get only certain modes that resonate inside of the box. And so there's in the hydrogen atom you have both the radial and then the angular conditions, 1 for each of the angles. So there's 3 quantum numbers that relate to the quantization in each of those directions. So I wanted to take a little time out to talk about something that you probably remember. Dr. Padilla has been starting using Physics for Realists to teach the Physics 1 and Physics 2, so Physics 2 in the spring. And I used to teach that course, and he was a student of mine back in grad school when he was in grad school some years ago, got his PhD, went away, did a postdoc, came back to join the faculty here, And he's been excited for years to learn how to use physics for realists. I was just starting to use it when he came back. And he's been working hard to get to the point where he could use the textbook. But he told me recently, he made a really good point. He says, the students in the class, PFR makes so much sense. If you're learning physics for the first time with PFR, it just makes a lot of sense. And he says, they don't understand the suffering that we had to go through because of learning it the other way. So I kind of paraphrased it here. I think this captures it. Those learning physics for the first time through physics for realists, like learning quantum mechanics for the first time, really. You can't know the joy shared by those who suffered first through the equation only approach. So I learned quantum mechanics, the equation only approach, just shut up and calculate. You can't really understand this. Here's how to calculate things, and we can compare to experiment, we can get it done. But you can't really understand. That was kind of at the heart of it. And so those of us who have gone through that, when we get to PFR, it starts to just crystallize and make sense. It's just so beautiful. I'm trying to share the suffering with you to give you some idea. You don't have the full appreciation of the nuttiness that there is in a lot of presentations of quantum mechanics, and the idea somehow that you've got to learn this and just kind of live with it, get used to it. But you don't have to get through it. You don't have to suffer through it. You don't have to put up with the nuttiness. But I want to warn you, though, that when you talk about quantum mechanics, if you take quantum mechanics in other courses, you talk to other professors, this is all very new. And it takes time for change. You know, like Dr. Padilla, Dr. D, those who have gone through it, they learned it. It takes time for change, right? And people have to understand the need for the change because they're kind of used to things the way they are. They have a kind of impetus in a way to just keep doing things the way that they used to doing. So I wanted to give you some idea about what it is that you are going to encounter in other courses. And the Schrodinger cat paradox is one of the things that you read about. So I wanted to introduce you to a little bit of history. Let's see that you can kind of see this.
Can we?
Yeah, turn the light down.
Thank you.
Okay, so we talked about Einstein's involvement in quantum mechanics, photoelectric effect in the early years of the 1900s, more than 100 years ago. And he spent the next 20 years trying to get people to talk about and do more experiments in quantum mechanics. And he felt like he was frustrated and alone because he couldn't get people involved in it. But finally, Compton had done his experiments, and there was more theoretical work done by various people that you can see in this picture. And then there was a series of conferences called the Solvay conferences. And this is the most famous one, 1927. You've probably seen this picture before. If you haven't, it's time you've seen it. Because these are the most famous physicists of the era. Einstein is down in front, central row, because he's the one who's prompting people to get to work on it. And there are a lot of other people that we've talked about. Here's Max Planck. There's Bragg. He did the diffraction of electrons. Let's see. The ones we've talked about, Ehrenfest we mentioned briefly. Paul Dirac, young Paul Dirac here becomes famous for the Dirac equation and the prediction of antimatter. Working in quantum mechanics. Here's Compton. There's Schrodinger in the back row, pretty young also. De Broglie, I'm not pronouncing the name quite correct. Max Born, we talked about Born and his granddaughter. See, Pauli, we haven't talked about much, but we will next semester. Heisenberg is up there, very young Heisenberg. Bohr is over here. So they're not all there. There are some notable people missing, but these are some of the most famous physicists of the era, all together in one place for a couple of weeks. Talk about quantum mechanics. And there was a lot of discussion in between the talks. Einstein, as I told you, had developed a rather complete quantum theory of light, but he wrote it up and then he stuck it in the drawer. He never published it. Discovered later. He'd written this paper, but he talked about it a lot to people to try to get them interested in the subject. So he had his own specific understanding about quantum mechanics, which has led to the textbook that you're reading now. And then Heisenberg and Bohr were Bohr was an established physicist in Copenhagen. Heisenberg was a student who went to study under him and developed in that time his own quantum mechanics. And then Schrodinger felt he was completing the theory of de Broglie. De Broglie's back here. De Broglie had some quantum theory that was complete, but to a certain level. But Schrodinger understood his equation to be completing the theory of de Broglie. So all of this was being discussed at this conference. And a famous part of it, well, actually, Einstein never really discussed the conference afterwards, but he would, publicly at least, but he would write letters. He and Schrodinger kept writing letters back and forth because they kept talking to Bohr and Heisenberg. Whose ideas were quite different. And Einstein and Schrodinger thought they were really pretty irrational. It just didn't make a lot of sense. So they wrote back and forth letters to each other complaining about, can't talk with these guys. After the conference, Heisenberg and Bohr talked publicly about it, and they kind of implied that Einstein was just kind of an old fart. He just couldn't understand the new stuff. They had these, what they thought were radically new ideas that were pushed upon them by the discoveries of experiments. And so they thought a radically new physics had to be developed, and that in fact, that certain basic principles just were disproven now by the new quantum. So it was from letters. Well, here are some of these people. Copenhagen. Interesting histories of all these people, by the way. What happened to them after the Solvay conference? Einstein lived to 1955, and he worked continuously all of his life on a lot of different things, but was still concerned about quantum mechanics to the end. Heisenberg became involved in the Nazi bomb project. He was the lead scientist in the development of nuclear weapons for the Nazis. Bohr was half Jewish, and they didn't get along real well after the war started. Denmark was invaded by Germany, and Heisenberg came to visit Bohr. Famous meeting about why are you here? Very interesting. Anyway, there's a lot of interesting history here to these people, what they did after this conference. But one of the main topics of the conference is what is the meaning of all of this? What the Schrodinger had this wave function. What does it mean? What does the Schrodinger equation mean? And Einstein was concerned about one of the threads of the discussion is captured in this quote. And so forgive me for reading it to you, but it really captures the essence of one of the conflicts between Einstein and Schrodinger and Bohr and Heisenberg on the other hand. So the attempt to conceive quantum theoretical description as the complete description of an individual system leads to unnatural theoretical interpretation, which become immediately unnecessary if one accepts the interpretation that the description refers to ensembles of systems and not individual systems. This is the beginning of the ensemble interpretation. Einstein is understanding what the Schrodinger equation gives us is predictions with regards to ensemble measurements, which you've heard over and over again in this class. Okay, but what this textbook doesn't talk much about, not explicitly, it does mention in a couple of places the error that some people attribute to this. Einstein is talking about the so-called, what he calls the unnatural theoretical interpretation, which is the Copenhagen interpretation. It's given a name of Copenhagen interpretation. And it's what Bohr and Heisenberg were promoted. And what Einstein and Schrodinger thought was kind of nutty. But it has, oddly enough, it has a lot of contradictions in it. And Einstein poked a lot of holes in it, Einstein and Schrodinger. But in spite of those contradictions, after the Solvay conference, it became mainstream. It's what's in virtually all quantum textbooks now, even though most physicists think it's wrong. It's a really strange sequence of events. All this history that has developed. I've been giving talks about this recently, and I start off with a review of the Copenhagen interpretation. And most of the faculty in the room say, "Yeah, but nobody believes in the Copenhagen interpretation." And so I point out, why is it that every single textbook, with the exception of 2, teach the Copenhagen interpretation? Nobody believes it, but that's all we teach. And when you really get down to it, when they're doing calculations, they're thinking Copenhagen interpretation, even though they're saying we don't believe it. But that's what they use. Okay, so what is this Copenhagen interpretation? What Einstein says is unnatural. So the first thing is that the wave function describes states of individual systems. That's the first problem, part of the aspect of Copenhagen. Not ensembles, but individual systems. And there's 2 physical processes that are described by the Copenhagen interpretation. The first is, so Roger Penrose has named these SE and R. So SE is the Schrodinger equation. It's just the Schrodinger equation gives the evolution of the wave function under normal circumstances. But there's a special thing here called the collapse, or Penrose refers to it as the reduction. When you look at a system, the wave function collapses. You make some observation, some measurement, the wave function collapses. And this is not governed by the Schrodinger equation. It's not governed by any equation. It's really a strange thing. There's nothing else like this in all of physics. It's very special, and it's what Bohr and Heisenberg injected. They just assert this without any kind of proof. There's no experimental evidence for this being a physical process. Schrodinger equation makes lots of predictions that can be verified. This thing is very different, but it's an integral part of the Copenhagen equation. So this idea of the state collapse, Bohr and Heisenberg talked about it some. Neumann and Dirac developed a mathematical formalism where it's part of the formalism, and it's what you'll read in most textbooks. The collapse occurs. Textbooks will mention ensemble. When it comes to a measurement, the measurement collapses the state. That's what they say. Collapses the wave function. Okay, we'll talk about this more next semester, by the way. We don't have time this semester to go into this, but if you're in the modern physics class next semester, we'll talk more about measurement. Yes.
So von Neumann and Dirac believed in this school,
Well,
along with Bohr and Heisenberg.
Yeah, that's a good question. It's not clear about von Neumann. I mean, what he wrote was clearly, he seemed to think that the collapse was a necessary part of the formula. But he said, apparently to other people, it's just a convenience, which makes it sound like some kind of approximation that can go wrong. Okay, so it's not really clear what he thought about that. And Dirac was very mathematical in his approach to physics, as was von Neumann. And Dirac, again, was often not so concerned with things other than the mathematical formula. So you can see how this is developing into an equation only thing. You have these equations, and this is part of the system of equations. It's not an equation itself, but it's a step that occurs in the calculation. So virtually everybody, professional physicists who have been through the training, anybody's taken a course in quantum mechanics at the college or higher level, has learned the Copenhagen interpretation. It's really hard, really takes a little challenge for people to see that in themselves. When I have a conversation with somebody, I was at Kimmer yesterday and I gave a talk. And the guy kept as he was talking, he kept collapsing the wave function. I kept pointing it out. Why did you do that step? And everything he described, he kept collapsing, and he didn't even see it himself that he was doing. It's very hard to unlearn these habits. So we're not even thinking about it, really. So a textbook that is commonly used, this is a very popular textbook. It's really good in many ways. But when it comes to measurement, there's a specific chapter on measurement. It's full of this kind of stuff. Suddenly it gets irrational. This is the weak point in the whole thing. So various statements in the Copenhagen interpretation, the particle isn't anywhere until you look at it, right? And Einstein famously said to a friend of his, they were walking on the beach complaining to each other about this nonsense. You really think the moon's not there if you don't look at it? This doesn't make any sense. But this is part of the Copenhagen school. This statement by Griffiths is something a lot of people think. Experiments have confirmed decisively the Copenhagen interpretation. That's just not true. It's something you can see and hear a lot, but it's just not true. Specifically, the wave function collapse. The Schrödinger equation, yes, not the collapse. The measurement causes collapse of the wave function. And Griffiths acknowledges this doesn't make any sense, but he's unable to, as he says, exercise this ghost. It's just stuck in his head and he can't see his way around it. It just becomes habit. Another textbook, I've used this one. I've used Griffiths too. I've used this one. This one is used pretty popular as well by Morrison. So he says it very clearly. A measurement of an observable causes the state to change in a way that's inherently uncontrollable and unpredictable via mechanism, the nature of which we don't know, which is this collapse. That such a change takes place is not an issue, which is wrong. It's very much an issue, has been ever since solar economy. This phenomenon is built into quantum theory. That's true in regards to the Copenhagen. What people have learned, it's definitely integral to that, but it's not really, doesn't have to be. In fact, I'm going to show you here, I'm going to talk about a problem that comes from this. But then there are other statements in total. The electron arrives at the detector, doesn't have a position. A measurement of some observable will collapse the state into one of the eigenstates of the operator. Microscopic particles don't have well-defined physical attributes until a human mind perceives that they do. This is really strange stuff, right? It's very unlike anything else in physics. So I'm going to examine some of these statements. An electron is both particle and wave. You probably heard that. This is all part of the Copenhagen. Electrons don't have well-defined trajectories. In the double slit experiment, an electron goes through both slits. Electrons in an atom don't have well-defined positions, but they're smeared out into the electron cloud. If you're talking about the electron cloud and smearing, not really anywhere, just everywhere inside the atom. Chemists are especially bad at using that kind of language, but physicists use it too. Okay, so there have been a lot of problems with this, and some of which are captured in what's called the measurement problem, which is an inconsistency in the Copenhagen interpretation. Einstein wrote to Schrödinger about this thing. If you're not looking at it, it's not, maybe not even real. Einstein says, I wonder if they put their money in the drawer in their bedside table at night, if they're worried that money might not be there in the morning, referring to Bohr and Heisenberg. Maybe it just kind of goes away or something. So Schrödinger takes that and he soups it up. He gets all the credit for it. We call it the Schrödinger cat experiment. This is on Wikipedia. But he's taking off from Einstein's letter. Okay, so in case you haven't been through this, let's go through it. You have a box and you take a live cat, put the cat in the box. Also in the box is a radioactive isotope, one nucleus. And there's a detector that can detect it when it decays. It's a radiation particle, alpha particle, or something, beta particle. It has a detector, and the detector, if it detects the decay, it smashes a flask of poison. which will kill the cat. And then so you close it up. And you wait. Don't look at it. Can't look at it. If you look at it, it changes things. So you can't look at it. And if you wait then for a while, you wait a half-life for the decay of that radioactive isotope. So in theory, if you had an ensemble of these, half of them would be decayed and half would not. But we're not talking about ensembles. We're talking about one. Okay, so you close it up. Now, according to the Copenhagen interpretation, the cat is now both alive and dead until you open the box. And then it collapses to one or the other. You can see why the collapse is coming about, because you're talking about an individual system. So this little experiment was devised by Schrodinger after communicating with Einstein. Einstein liked it a lot. He thought, yeah, that's a good way to say it. These guys just don't make a lot of sense what they're saying about quantum mechanics. It doesn't make a lot of sense. And they thought that would be the end of it, right? This just shows that it's kind of nutty. Oddly enough, this if you look on the cover, Griffiths, there's the cat. Griffiths uses this to demonstrate to you that your common sense is just wrong. That you think the cat has to be either alive or dead, but that's just wrong. Quantum mechanics is telling us that the cat is both alive and dead. Okay, and that's the way it's taught. So you're refuting your common sense. PFR, remember, builds on your common sense and says that's where we have to begin. And we're going from there and walking very slowly. Okay. So Einstein and Schrodinger thought, well, that's clear evidence against it, but it survived and it became part of the teaching paradigm.
I wonder if Schrodinger rolls in his grave because of it.
Right there. He said, if I had known it was going to come to this, I never would have gotten involved in the first place. No, that's his most famous contribution to physics was the Schrodinger equation. But their interpretation of what it means to him was just nonsense. It didn't make any sense. And the fact that somehow the Schrodinger equation was all wrapped up in this. I talked to a high school teacher one time, was talking to him about quantum mechanics, and he had read something on quantum mechanics. He said the Schrodinger equation says the cat's both alive and dead. He said the Schrodinger equation says the cat's both alive and dead. So I wrote the Schrodinger equation. I said, okay, can you tell me where the cat is alive and dead somewhere? I just don't see it. Okay, so there's been a lot of work on this over the years. About 4 years ago, there was a pair of physicists in Switzerland that it's effectively just a more specific case of the cat paradox. And it's kind of done in a way that's more appealing to physicists. But it shows that there's a contradiction in the Copenhagen interpretation when you have the wave function collapse. Under certain circumstances, it's a very complicated experiment. I'll take a minute to describe it to you. So there was have a box, but instead of having a cat, you have an observer. Who is this was invented by a guy named Wigner, famous physicist named Wigner. Wigner's friend is inside the box, and instead of a radioactive decay, he's got some kind of measurement he's going to make. Maybe he's got another box inside. He's got something that's like a cat inside the box. The friend is inside a box himself, and Wigner is standing outside, watching the whole thing. If the friend collapses the cat by opening the box, Wigner thinks they're still all superimposed. So the state is a superposition, like you've learned about. The alive and dead is their interpretation of the superposition of two states. So there's a contradiction between Wigner and his friend. His friend thinks it's collapsed. It's one or the other. Wigner thinks the cat's still both alive and dead. There's a contradiction involved in this. So these two physicists in Switzerland, they double down on it. So there's a cat in here. Okay, but now the friend here observes the cat based on his observation. He prepares another box, which he inserts into this second setup. So there's another friend, there's another cat, and there's another Wigner. And it gets kind of complicated. It's a difficult paper to read. It's very convoluted. But there are all these steps. Wigner asks his other Wigner over here, he asks this friend, and they can communicate with each other. And based on that, these guys come up with contradictory predictions about what's going to happen here when it's opened up. So that just shows that the Copenhagen interpretation with the wave function collapse is not really about physical theory because it makes multiple predictions that are in conflict with each other. There isn't any prediction, in other words. It's multiple conflicting predictions, so it's not a prediction. So it's not a viable physical theory. And this is deeply rooted, the problem with this is deeply rooted in the wave function collapse and the idea that the quantum mechanics is not a statistical theory. That's the Copenhagen. Okay, so, but you're familiar with the ensemble interpretation. So it's not just using ensembles, but using them completely through. And we'll see that more when we talk about measurement next semester. So we'll get into this quite a bit more next semester. But we have no wave function collapse. Measurements are done on ensembles. The evolution of the wave function is given by the Schrodinger equation. And that's it. You never need anything else. There is one thing important, that the measurement involves an interaction between the system and the detector. And that has to be put into the Schrodinger equation. There is a Schrodinger equation that governs the interaction of the detector with the system. And that needs to be included. So the measurement is itself a physical process described by the Schrodinger equation. That's why there's no wave function collapse, because we know how things interact. And so we haven't talked much about how our measurements actually done. We just talked about them in general abstract term. Next semester we'll give some examples of measurements and how they're done. And there's a Schrodinger equation that describes multiple entities together. We've only done one thing at a time, one electron. So now we have a detector and the electron. Now we have to describe the system of both together. And so we have to deal with two entities or more entities. How do we extend the Schrodinger equation to include multiple entities? That's what we haven't done, and that's what's coming. So there's no collapse. Okay, so, and you've learned this, the wave function gives probability and more. We looked at the momentum distribution, for example. And so what I'm going to show you is how some of those previous statements that we saw actually should be understood. But the point is that with the Copenhagen interpretation, you're left saying things that are meaningless. That sentence, this statement is false. Think about that for a minute. It obviously doesn't mean anything. Right? If it's true, it's false. If it's false, it can't be true. It doesn't say anything. There's some words stuck together. They sound like they ought to mean something when you put them together, but they don't. They actually mean nothing. And that statement, cat is both alive and dead, is actually a meaningless statement. It doesn't mean anything. It just sounds like it ought to mean something. So the idea is to say, in physics, to say meaningful things and not to say stuff that doesn't mean anything. Like Elvis is alive in a parallel universe. It doesn't mean anything. Okay, so the electron is both particle and wave. That's what you hear in the Copenhagen interpretation. The correct thing is that there are two entities involved, a particle and a wave. They're not the same thing. One thing can't be both particle and wave. It can't be both localized and extended. So the way to realize that is that there's obviously present in the experiments two things, the particle and the wave. It's not the same thing. They're associated with each other. They're interacting with each other, but they're not the same thing. Electrons don't have well-defined trajectories. Well, they do, but they're also moving under the guidance, the influence of this guiding wave structure, which is not explicitly present in the Schrodinger equation. we have some potential energy, some potential particle in the box, or some harmonic oscillator, a barrier. The electron is moving under the influence of that force, but also the guiding, and that's not explicitly in the Schrodinger equation, but it's there implicitly in some way that we don't understand. But that has both interfering resonating part and stochastic part, which helps us to understand what's going on. Why the particle can make it through a barrier when it shouldn't have enough energy. It's said in the double slit experiment that the electron goes through both slits. One electron goes through both slits. Shoot an electron through, and it must go through both slits. Well, if you recognize that there are two entities involved, it's clear that this nonsense statement can be expressed better, that each electron goes through one slit or the other, but the wave goes through both. No problem. Interference comes from the guiding wave, which interferes with itself like waves can do. Electrons are smeared out into an electron cloud. It's not true, but there is a kind of averaging over the motion of the electron. We were talking about electron orbits last time, about the nature of these electron orbits, and averages over them. And again, when we're doing measurements, what we are observing is averages. The cat is both alive and dead. The resolution is quite simple. Don't do just one system. Make 1 million copies. 1 million cats. 1 million radioactive nuclei. 1 million detectors. 1 million poison flasks. Close off each one of these boxes, all of them. And then, after some time, we open them all up. Half of them will be alive and half will be dead. There's no mystery. Kind of expect half of them are going to be alive and half are going to be dead. But there's none of this strange thing that's saying that each cat is both alive and dead until you look at it. Right? There's none of that. Okay, and we've talked carefully about ensembles, a little bit about preparation, and a little bit about disturbance. We're going to understand these in better detail. These are important things that most textbooks just gloss over, not clear about what they mean. So we'll go through this in some detail in next semester, but the point is that we don't have to say the cat is both alive and dead. There's nothing that compels us to do that. There is no experiment that demonstrates that. Okay, so again, the wave function describes an ensemble of identically prepared physical systems. That implies also that you need many experiments to be able to use the formalism of quantum mechanics. You need to be able to do reproducible experiments, because it only pertains to ensemble averages. So these statements are just wrong. Like this one, experiments have confirmed decisively the Copenhagen interpretation. It's just wrong. It's odd that we keep propagating this. And as I said again, a lot of the faculty say, "Oh, we don't like Griffiths. Griffiths is full of nonsense," but that's what they use. Right? When was the last time you talked quantum mechanics? I'll use Griffiths, but I don't like Griffiths. I don't think it's right. Okay. So that's the reason why I and others are high on this textbook, because it's based on developing principles and understanding physics from these principles, along with the use of the mathematical formalism, but understanding what the formalism contains and what it gives us, so that we can say meaningful things. So that brings me back to the statement by Dr. Padilla. If you haven't been through this nuttiness, you might not appreciate as much the beauty and the clarity that's in this textbook, right? And if you don't suffer through it, maybe you don't have the same level of joy. But so that's why I want to talk about explicitly about this, and also about what you're going to see when you go other places, because this is still being taught at most places. Copenhagen interpretation is still being taught at most places. It takes time to change. So, one day, I do expect Griffiths will be gone, and we'll be using Rizzi for the undergraduates. All right, thank you. Any questions about that? Yes.
what changes, the reduction, the collapse? What are they doing? Like, since they only have the equations, what are they doing equationally? What are they doing? Like you said, they somehow you said,
What does the collapse mean? How's it used?
so how did like,
Yeah.
what do they literally do? Like,
Let me
what's
show
an
you.
example?
I understand the question. Let me show you.
Yes.
So we've talked about superposition of a particle in a box. We talked about a quantum state, which is a superposition of the two lowest states, for example. We've worked on problems relating to this superposition. That's what's described, the CAD is described that way, as being a superposition of alive and dead. And you'll see a notation that I haven't introduced you to. We'll learn it next semester using these brackets. But that's another way of writing quantum states. And we're preparing here to also to do multiple entities, that is the CAD and the detector and the flash and all that stuff. So this is notation invented by Dirac, and it's very common. Not in introductory books, but at a higher level, like in quantum computing, they use this notation all the time. They don't use this. So this is the superposition, right? So what is meant by this is what we were talking about here. This is a quantum state, which is the superposition. The guiding wave structure is not just the superposition, but there's some kind of, the guiding wave structure is different when it's in the superposition than it is when it's not. Okay, then you make a measurement. These are energy eigenstates. So let's suppose you make an energy measurement. So according to the collapse, it becomes, if you see the energy is equal to the energy of the first state, then the wave function collapses thereafter to that state. Or if you measure an energy which is corresponding to the second state, then the wave function thereafter corresponds to that state. It becomes a pure mode. This is not a pure mode. The measurement reduces the wave function to the pure mode that's associated with the measurement value. That's the collapse. In the case of the cat paradox, when you look at it, when it becomes either alive, they get rid of half the wave function in the measurement process. That's what they say. And that's the error. That's the step. All you do is just change the wave function to this thereafter.
That's literally, wow, that's literally what they do.
Yes.
Silly.
So what's missing here is, let's look at the detector. Let's suppose Wigner's friend is looking inside the box. He opens the box up. The problem is that what we're representing here are also just the system itself and not the other factor, which is the observer or the detector. So the interaction in what we'll learn in the ensemble interpretation is that there's an entanglement between the detector and the system being observed. And I haven't taught you yet how to write multiple wave functions for multiple things. So you have to have a wave function that combines two things, not just the electron, but the detector detects the electron. And the correct expression is after the observation that there is a coupling between, let's see how to do this, a coupling between the particle, which is being detected, and the detector. So then you have a wave function afterwards, which describes both together. So the detector, in this case, the detector will have registered 1, and the particle is now in this state. Over here, the detector will detect 2, and the particle is in this state. So, or in the case, well, let's just write it like this. Now I have introduced you this notation. But you can see there's a combination of the particle with the detector state and the particle with the detector state. And after the observation, they become entangled like this. All all this represents, again, in the ensemble, is half of the system will have measured E1, and for those, they are in state 1. And for the other half, the detector says E2 when it's in that state. But the state is this superposition, not this reduction to this. So you'll see how that works. So that's the step. The other thing associated with this is, you remember the square of this is probability. So there's a probability of 50-50 that you'll get one or the other, alive or dead, 50-50. The square of this is the probability. The square of this. If it's after a half-life. Okay. So that's what they do in the formalism. And it's a strange step. There's no physical process associated with this in the collapse. But with the proper way to do it is to recognize that the detector is interacting physically with the system. And that's what gives rise to this. So you'll see that next semester. It's recognizing that a measurement is a physical process. One thing interacts with another, and that's governed by the Schrodinger equation. You have to have, in the Schrodinger equation, you have to take into account the interaction between the two. So we have to understand how that works. Other questions?
Since you mentioned the modern physics courses, what textbooks other than PFR are we using?
Not sure yet. Yeah, I'm still working on that. Yeah, we'll use the PFR mechanics. I'm trying to figure out a way to use. I'm sorry, we'll use the PFR quantum mechanics. I'm trying to find a way to use the chapter on special relativity that's in the mechanics. It's a beautiful understanding of special relativity. There's a corresponding chapter in the E&M book that we didn't do, also on relativity. It's the next chapter after we finished, where we got to the book in spring. So I'm trying to figure out a way that we can do those, get course packets where we can put those chapters in. And then I'm not sure what I would do for particle physics. There's a small book by Robert Took that's pretty good. Might use that. There'll be a noticeable difference between PFR and not PFR, right? But there's still stuff to learn. So I'm also thinking about, well, there's some other thoughts, but I don't really have a good answer to your question yet.
Okay.
I'm hoping to do that this week.
I was asking because I looked over like the courses, like all these different things.
Yeah.
It's like, oh, it's about to be like a bunch of textbooks that we have to buy.
No, it will be, there may be a course packet or a couple of chapters from PFR 4. And there might be a small textbook on particle physics, but those would not be very much. So the principal textbook is going to be the quantum mechanics. That gets into measurement theory, it gets into ensemble, it gets into entanglement. So we'll study entanglement. And we'll touch on what's called the Einstein-Podolsky-Rosen experiment, the EPR experiment, which is a very interesting understanding of how particles at distance can influence each